Hey, Honors Physics, this is Mr. Hausman. We're going to take a look at continuing our study of E-fields, electric fields, and you can find us on the bottom of page number, oh shoot, it's not numbered, I think it's page number 4. So, one class didn't quite get a chance to examine this, and I think in D block we actually rushed it. So we're going to kind of just re-summarize what are the key principles, maybe they're called laws for drawing vector fields. Okay, so field lines are completely fictitious. Electric fields are invisible, but when we want to depict them on paper to describe them, we call it field line diagrams or field line drawings. And these are represented as vectors. They show the direction of force that a tiny positive charge would experience. And there's a name for this tiny positive. And you're like, yeah, of course it's a proton. Well, in the field of, in the study of electric fields, it's called a test charge, and it's always implied to be positive. Now, can you pretend there's such a thing as a negative test charge? Yes, but by a lot of standards, a test charge is a small positive, meaning like a proton. So the direction of the field lines always has an orientation. They point out of a positive and they point into a negative source. And you can see this in the picture, but the arrows are often very small. So you can make them bigger if you want to make them more visible. So I'm going to do that to kind of show they're out of the positive, right? Out of versus in toward. And that's the direction of the field lines. So the line density, how close the lines are together, shows how strong they are. So if someone kind of said, well, how close are the lines here? Close to the source, you would say, yeah, those lines are closer together than when you were to examine this position. There the lines are farther spread apart. So the closer the lines are, the stronger the electric field. So close together means stronger. E-field lines never cross. Instead, they can curve, they can bend, but really what's happening is when you start having complex shapes and the field lines might start to cross, instead what we're going to do is we're going to do vector addition and find out how they actually create vector sums. Okay? Lastly, one of the key principles, and it's not least, right, last but not least, is that the direction of the field line should always be drawn perpendicular to the surface. So if you have a surface like this and it's got a charge on it, and we know that charges, field lines come out of positives, so therefore, if I'll pick a new color, what's perpendicular to a surface? Well, it would be pointing out here, perpendicular, pointing out here, perpendicular, and pointing out like this. And that's why we get that starburst kind of shape, or sun rays kind of shape. Something happened in the production of this video, and I had to redo this page, but we'll start kind of again, and I apologize if there's a little jump between the two pages. So on this page, we're going to now get some practice drawing vector addition, and that's really what the principle of superpositions is. We're going to do vector addition of E-fields. And what is point P? Well, P is just a point in space. That's why it's P. And we're going to think about drawing the field lines either away from or toward the source through point P. Now, the most correct way to draw this is that, of course, for an electron, the fields go in all directions. But we're not really interested in what happens out here or out here. We really want at point P. So we're going to extend this line out through point P. Now, a positive charge, on the other hand, doesn't go inward. Remember, the field lines go out. And I'm going to extend this one out through point P, ideally with a ruler. Okay, so what I notice is that at point P, one vector coming from the positive source is going northwest, but there's another vector that's going southwest, and they appear to be kind of balanced angles. And I know that when I do vector addition, the north component of this vector and the south component are probably going to cancel out. And what it's going to lead to is an electric field at this point P that when you add them up, it's really just going to be a west vector because the north and south will cancel. Now, likewise, what if you have two charges, but they are the same charge, right? They're the same. Well, let's see how it's going to be different. So negatives, the electric field lines point in, and for the other charge, the electric field lines point in. And I'm going to label those kind of just using everyday common language. This is southeast oriented, and this is southwest oriented. In this case, it's not the norths and south components that cancel. I bet some of you can see that instead the east and west are going to cancel, and what you're going to get for a net result, sorry about that, is a strong, basically vertical electric field. And that is what happens when you have similar charges, either both positive or both negative. Okay, if you go on in physics and start examining even more complex fields, you're going to notice that maybe you have three charges, and all you have to do is do the vector sum. And so out of positive number 1, the field going through point P would be oriented perpendicular to the surface, going out, and then there would be another vector from Q3 kind of going in the opposite direction. But then Q2 is negative, so that means the field line goes in toward it. So do you notice that this vector and this vector are equal and opposite strength because they're the same distance from point P and they're going in opposite directions, so they cancel out. And so our E field would actually be in toward the negative. And that would be the net E field or the total E field. So that leads us to, what does it look like when you start mapping out many points in space? So when you have opposite charges, remember we said it was horizontal when we're at the halfway point? And it is, but it's actually part of a greater curve. And the closer you get, the tighter the curve is. And eventually at the middle, it would actually be straight across. And then the curves get wider and wider on the other side. So it kind of looks like a spider shape or maybe multiple legs coming off of these guys. But notice, for the negatives, they go in, and for the positives, they go out. But because they're opposites, they connect. Similar charges, two positives or two negatives, have a common pattern. And you may remember above we said that the E field is vertical. And that's true. Let's use blue for that. And it is vertical, but it's actually also, and I'm going to use a word that some of you know well, it's asymptotic. Do you notice that the E fields approach the vertical, but they don't seem to get there? But is it obeying the laws? Yes, these field lines are coming perpendicular out of the surface, but they are not crossing. They are curving due to vector addition, and the field lines will never cross. Now, it leads us to one observation, right? There's a vertical line they don't cross here as well. But here's the observation. Do you notice the gap in the middle, regardless of whether it's two positives or two negatives? And that's referred to as a zero field region. Well, zero field, how can you have none? Well, if you were to add the two component vectors, right, for two negatives, there would be a vector in to the left negative and into from the other direction into the right negative, and these two vectors cancel each other out, and that's why there is a zero field, E equals 0, in the center of these regions. Lastly, what happens if the charges are not balanced? What if this one has a larger Q and a smaller Q? Well, it kind of makes an imbalance in the curves, and you notice it doesn't actually go vertical, but it obeys the laws that the lines come out perpendicular and the lines never cross. These kind of diagrams are best calculated with computers, with matrices, and with, of course, animations or computer graphics to represent them. Here we would have a larger Q, but it's negative, and a smaller Q that's negative, so we've got smaller there. Now, if they're opposite charges, they still connect, but the shape is not balanced. You could probably come up with names for these shapes, but they could still connect from positive to negative, but none of the lines cross. Okay, one of the last pages of notes we're going to do is about ideal diagrams for electric fields. Now, we've never heard of plates. These are called electric plates. Plates are nothing more than flat pieces of metal, maybe attached to a negative end of a battery or a positive end of a battery or a power supply. And what you do is you do exactly what you might think. You apply the laws that we talked about on the previous page. So electric field lines go in toward negatives. And if you don't remember that, you just ask yourself, what would a proton do? What would a small test charge do? Now, you might notice I did not tell you how dense to make them, but I tried to maintain them evenly spaced out. Now, on the other side of the plate, remember, field lines go out through infinity. So we actually draw them right through the other bar. Okay? Now, what about at the ends? Do they curve? Do they bend? Well, at that very curve, it's kind of weird, right? Perpendicular to the surface should be here. And then I guess at the very corner, there should be a bend. But we're going to talk about what happens at the ends. So I'm going to erase that for now. I don't want to get too deep in yet. Now, that's only the field lines for the negative charge. Now, I'm going to switch color and show you what would the field lines look like for the positive charge. Well, they go out of positive, right? So down here, they'd be going out, away from the positive plate. Almost pretend the blue lines aren't there. I only drew 4 this time. If you can fit in a 5th, that's great. And then out of the positives. And notice I'm going right through the other plate because the plate's not going to stop the E field. E fields go through stuff. Now, what happens? Okay, let's do superposition. Let's do vector addition. What happens when you add the reds and the blues here? They cancel out. What happens when you add the reds and the blue here? They cancel out. What happens in the middle? They don't cancel out. I notice my reds and blues are pointing in the same direction. So what you get is actually an incredibly strong electric field that is completely parallel between these plates. And notice I increase the density because it is a strong E field. There is a zero field on the outside. And in theory, at the ends, there's a little bit of curvature. A little curve on the ends, but through the middle of the plates. So those are called parallel plates. And for some of you might know that that's actually a piece of electronics. That is the principle for how to make what's called a capacitor. If you've never heard of a capacitor, we'll study that shortly. So now I want you to do some drawings. Parallel plates you had never seen. Now we're going back to single positives. But then this drawing has 3 charges on it. It doesn't mean it's 3 objects. It means it's 3 times the strength. And what should that do to the density of the field lines? If it's 3 times stronger, it should have 3 times the field lines. You are going to practice and complete this part, remembering that field lines go out of positive. They go in toward negative. Okay, now this is a system. I want you to see if you can just use the previous page to kind of draw in your best version what would happen to the field lines between a positive and a negative. And you can look back on the previous page if you want. Okay, this page is part of the assignment today. I want you to complete page 7. These are questions where you put in the approximate amount of charge that you think each one would have. Here's a visual problem to do, right? This one we're saying which one is incorrect. One of those pictures is wrong. Here's a student who's making an error, and we're going to help them figure out what's wrong, and you're going to explain it. And likewise, you're going to figure out what's going on here. So there is a zero field inside a conductor. That one we hadn't talked about yet, but inside a hollow metal conductor, there's a zero field. Okay, so I'll help with that one. Lastly, as your assignment today, here's some reference pages that are really just important configurations. We're going to come back to light fun in just a minute. Okay, we're going to compare fields over the next few days. The last part of your assignment today is to answer these questions. Okay, so an electric field shows the direction of force, right? An E field shows the direction of force on a positive charge. So therefore, if you put a positive into an E field, you just basically say that a positive goes in the same direction as the E field. A negative goes against the E field. So forces on a charge, right? On a charge points, right? So which direction does the force point? It's the same direction as the E field for a positive charge, but it's against the E field for a negative charge. It's just another way of summarizing it. And this will be something that you're going to practice. So on this page, I'd like you to take a look on 11. An electric field points right. Let's just draw that. And a positive charge is moving in that field. Well, which way is it going to get pushed? And all you have to do is remember that positives go with the E fields, so it would go to the right. Give it a try. Page 11. That's going to be enough for today.